All right, so this section is where we're going to put some of those factoring skills to use. So again, we're going to talk about polynomial functions and their models. So first thing we're going to really focus on is determining the behavior of polynomials, using what was called leading term tests. So we're talking about long-term behavior, and then we're going to factor polynomials and find their zeros and their multiplicities. So that's something we call like short-term behavior. And then we're going to solve applied problems using polynomial models. Sorry about that. Oops, looks like part of my slide cut off here. All right, not sure what happened on the bottom there, but here we go. So a power function, which is one of your polynomials, but we're going to start here with a power function. So your power functions are of the form kx to the power of n. K is going to be any real number. X is going to stay a positive integer. So with the exception of y equals x, the graph of a power function with an odd power is going to look like cubics. So I mean, it'll look like one of these. So this could be x cubed, this could be x to the fifth, this could be x to the seventh. We can keep on going. So as long as it has an odd power, that's what's going to look like. And then if k is positive, so if like say k was 2, let's say 3 here, 8, as long as what's out front here, that coefficient is positive, it's going to start from your negative numbers, increase, and then keep on going to positive infinity. If you have even powers, then it's going to look like a quadratic. Do some blue. So it'll look like one of these ones here. So this would be an example of like x squared, x cubed, sorry, x to the fourth, x to the sixth, etc. And then once again, if I put positive powers out here, or positive coefficients, let's see, 2, 8, 1, doesn't matter as long as it's positive, then it's going to look like this. So when you get your negative coefficients, what's going to happen is that each one of these graphs is going to reflect over the y-axis. So that's how your even powers end up opening down like this. So like I said, this is if you have negative coefficients out front. As long as that degree is, or power is a even number, it's going to leave it a parabola. What that coefficient does, if it's positive, it opens up. If it's negative, it opens down. If you have your odd powers, then what happens is it doesn't go from an increasing function, it turns into a completely decreasing function. So once again, it flips it over the x-axis. So if you had negative coefficients, that's what you would be seeing. So we talk about this because a lot of the behavior that we see with long-term behavior and what we see in short-term behavior is largely governed by your power functions. And it's governed by what we know about these power functions. We know we get this shape if we have a positive coefficient and even powers, positive coefficient, odd powers, negative coefficient, even powers, and negative coefficient, but odd powers. So a polynomial function is going to be given roughly by like, this is sort of like a general form here for your polynomials. You'll have a coefficient and then x to a power, another coefficient, x to another power. And ideally, this one out here is going to be your highest power. So this is the one that we call the leading term. So if my polynomial happened to be, say, 5x to the seventh, 3, and then ideally it would come after that would be the next lowest power. And then your next lowest power. And you may end up having to skip one, like maybe there isn't an x to the fourth. But ideally it's like this. So you would keep your your terms, the powers of those terms would go from largest to smallest, so descending in powers. Part of the reason we do that is because then we see this here is my leading term. Okay, so this is just kind of some sort of basic ideas of what you're going to be looking for with, actually, I think I got slide out of place here. Let me see. No, I think I just missed something back here. Sorry about that. Yeah, part of my slide cut off. That's what happened. That's weird. See if I can fix that. Okay, there. That was my problem. Stuff's disappearing off my slide. Okay, sorry, I opened up a different file. This one is working better. Okay. So like I said, these are your coefficients. Like I said, that first term is your leading term. What I wanted to say is that power out front of your leading term is called your leading coefficient. That goes a little too fast. All right, so this is just some sort of basic, kind of your basic shape here. So as we see, we have a quadratic. This is my leading term. Even though we have, like a odd power here and things like that, what we notice is it's still making that parabola shape. So it's following that leading term. Same thing here again. We have a leading term here. Is that x cubed? And we're getting that kind of that cubic shape. I've got caught. So cubics kind of look like this. So this one kind of goes up and down, but overall we see sort of that, basically it's that same shape. Because we're thinking in the long run, what is it doing here? In the long run, it's kind of keeping that same thing going on. So these are examples of polynomial functions. So you have your quadratics. So we got an x squared. You can have your linear equations. So sometimes they're straight lines like this. You can also have straight lines like this. So all your linear functions are your polynomials. You got your cubics here. This is to a power of 4. These are non-polynomial functions because that's absolute value. This would be an exponential. Um, this is that case where if we use a power that is not a positive integer, that's not a polynomial. We get this kind of like a curved V shape. And then here, this is a rational. So it's a little involved what continuous means, but a graph of a polynomial function is continuous and smooth. The domain of a polynomial function is always a set of all real numbers. So if you look at all of these and you think about that domain, well, this is just going off to infinity in both directions. So is this, this. So all these, we see a domain of all real numbers. So what we're going to really get at is what is long run behavior. So I have 3 lines on here. They all have the same leading term. It's just one comes after, it's a little different. So they all have that same leading term of 3x to the 4th. So the black one is just 3x to the fourth. The blue line is, I added another term to it, so I added on the 5x cubed. So generally has that same kind of shape. It's going up like this at the ends. So that's like we're talking about long run behavior. The red one, I had put two more terms on here, but we're seeing that generally, even though it bounces up and down, when you're looking in the long run, all these are doing the exact same thing. So though the graphs are not the same, what is similar about them is that as x is approaching infinity, the polynomials start acting like your leading term. So let me move the decimals for a second so we can see this a little better. So these are our three graphs again. So it's really, we're really in a small area here. So in a very confined space that we see that these graphs don't seem to look like anything like each other. There you go, that one had to be fixed. But what we're noticing is that as I pan out, that eventually out here, they start almost looking completely identical. Do this. So you see they start, as I keep scrolling out, they almost be looking like the exact same graph. So this is what we're really talking about with long run behavior, is that in the long run, all these functions start acting like their leading term. So all of them start acting like 3x to the fourth. So they start matching that black line eventually. So this leads us to what we call the leading term test. So if an to the xn is a leading term of a polynomial function, then the behavior of the graph as x goes to, so let me put this on here. This little arrow here means approach. So the graph as x approaches infinity or approaches negative infinity can be described as one of the four ways. So what we're meaning is that for going this direction, that's negative infinity. This direction is positive infinity. So we're talking about as my x values head out in these directions, what's going on here. And what we know here is that if we have, I'm going to write my leading term again, my leading term looks like this. If a to the n is positive, then it's going to be one of these two graphs here. If I have an even power, then what we should see is this little squiggle line's like just what's going on in the center. Like we saw there with the last three graphs, like when we get right in the middle, they don't look anything alike. So we're talking about way out here, going out to infinity, what do they start looking like? And they start looking like the same function. So what's going to happen is, like I said, your leading term is taking over. So if we know what that leading term is doing, because that goes back to those power functions, even coefficient, or sorry, even power, positive coefficient, it's going to be parabola that opens up. Even power, negative coefficient, parabola opens down, so it looks like in the long run. If I have an odd power and a positive coefficient, then it's going to stay this increasing cubic curve. If it's an odd power but a negative coefficient, then we get a decreasing cubic curve. So like I said, we're not concerned what's happening in the center of the graph. We're concerned what's happening out towards infinity. And out towards infinity, it acts like that leading term. So it takes on the attributes of its power functions. Okay, so we're going to kind of determine, we're going to have a set of graphs here, but which one of these would follow which graph. So what we're concerned with is what's my leading term telling me. So I'm going to do like a little sketch here first. So what this is telling me, and we kind of already saw this, I have a positive coefficient and an even power. So whatever it's doing, I don't know what's happening in the center, but at the ends, it should be opening up kind of like this. So for B, we got a negative coefficient. Change my board here a little bit. We have a negative coefficient and we have that cubic shape, that or odd power. So we know it's either going to look like this or it's going to look like this. So because it has that negative coefficient, we know it's this is going to start acting like. For C, we got a coefficient is 1. So we're going to say it's a positive coefficient, but the degree is odd. So it's my other option that B didn't give me. It's going to open like this, or it's going to have this in the long run. And then D, it's long run shape. We got a -1 out front, so negative coefficient and even power. So it's going to be opening down. So we have a basic idea of what this should look like. So if we were to match graphs, let me get rid of this part here. What we see here is we said A should have this kind of it'd be like a parabola opening up shape. So we see that D matches that. So let me erase my old graphs here. We have them down as a reference. Like I said, D goes as this one because we know it should have this kind of shape because of that leading term. Because of this leading term, we know it should look like this. So this would be B. For C, because of that leading term, we know it should be looking like this kind of shape. So we see that A matches that. And then for this part here, we know that this is going to be that parabola again, but now it opens down. So we see C matches this one. Okay. So I've provided you with another set on that worksheet. So work on problem number 1. Like I said, just pause for a second and try to match these graphs with, or these equations with the graphs. Okay, so once again, talking about those leading terms. So the first one's leading term is 4x to the 6th. So we got that positive coefficient in an even power. So it's a parabola opening up. So we should see something like this at the ends. So this would be C. For B, we got a negative coefficient and a positive power. So it should be opening down like we see over here. So this one matches with B. For C, let me see, we have a negative coefficient. We have an odd power. So it's going to be those cubic curves. This one's going to be the one that's decreasing. So we say D. And then for little d, we got a positive coefficient and odd power. So it should make that like cubic-ish curve, but this time it's all increasing like we see here with A.